Hello everyone, and thank you very much for the opportunity to participate in this first national conference on theoretical physics frontiers. My name is Ahmed Bisiri and I recently graduated with doctorate from the Faculty of Physics at the University of Babzawa. Today I will be presenting our work titled Impact of Quantum Particle Nature on the Mean Separation Distance, which was conducted in collaboration with Dr. Kamal Murad. Our objective is to develop a comprehensive theoretical framework that describes the behavior of quasi-particles existing between bosons and fermions. These particles emerging in two-dimensional quantum systems, exhibiting wave functions symmetrization that deviates from the traditional symmetrical or antisymmetrical forms. The study aims to investigate how their unique quantum properties influence the mean separation distance, giving rise to novel quantum effective forces and interactions. This presentation will be structured as follows. First, in section 1, we will introduce quantum particles, focusing on fermions, bosons, and anyons by providing an overview of their fundamental characteristics. Next, in section 2, we will compute the wave function of two non-interacting particle systems, exploring how the quantum mechanical description of these particles emerges. Finally, in section 3, we will analyze the influence of particle nature on the mean separation distance, examining how the characteristics of the particles affect the distance between them. Finally, we will conclude with some general remarks and perspectives. Let's start now by introducing quantum particles. In three-dimensional space or higher, it has been shown through the quantization of angular momentum that the algebra governing spin angular momentum is a non-commutative, and it is given by the present relations. The successive application of raising and lowering spin operator S plus and S minus on the state Sn leads to the condition that the spin quantum number S must be either an integer or half integer, leading to two main categories of particles, bosons and fermions. However, in two-dimensional space, specifically focusing on the z-axis as the only axis of rotation, the spin angular momentum is represented by the operator Sz, and verifying the commutation property. So, consequently, the eigenvalues of Sz can span a continuous range along the z-axis, including fractional values. This unique property opens up the possibility of particles in two-dimensional space, known as anyons, exhibiting fractional statistics. Then, for one-dimensional space, there is no axis for rotation, so there is no concept of spin, so there is no emergence of quantum statistics. As a result, in the quantum realm, particles are indistinguishable, enabling the creation of a wave function that generically describes states without specifying which particular particle occupies them as like, where for alpha equals to 0, it corresponds to bosons with a symmetric wave function. Therefore, an infinite number of bosons can occupy the same state. For alpha equals to 1, corresponds to fermions with antisymmetric wave function. Therefore, two fermions cannot occupy the same state. Pauli principle. And for alpha between 0 and 1, it corresponds to anyons with a wave function that is neither symmetric nor antisymmetric. So that by exchanging two anyons, the wave function can acquire a phase factor alpha pi, and this allows two or more anyons to exist simultaneously in the same state, leading to the generalized Pauli exclusion-inclusion principle, which differs from the Pauli principle in that it allows an arbitrary finite number of particles to occupy the same state. Let's imagine now that we have two non-interacting particles, both of mass m, placed in infinite square well defined by the potential V of x as follows. The time-independent Schrödinger equation could be, for the system, it could be written as a system of two free particles in the region 0 to L. It admits psi n and En as eigenstates and eigenvalues as follows. So the total wave function psi x1 and x2 for distinguishable particles is expressed as the product of the two wave function. However, for undistinguishable particles, psi x1, x2 is written as a product of the two wave function, but we take into account the permutation between them. As an application, and in order to gain insight into the spatial separation distance between these particles, we calculate the expectation value of the square of their separation distance, represented as the mean of x1 minus x2 square in the previous calculated wave function psi x1, x2. For distinguishable particles, the mean separation distance takes the following form. Whereas for undistinguishable particles, the formula includes an additional term that depends on the quantum nature of the particles, establishing a clear link between their nature and how they behave in space, where for bosons alpha equals to 0, cosine alpha pi equals to 1, and consequently the separation distance decreases compared to classical particles, indicating the existence of quantum attraction force between them. And for fermions, alpha equals to 1, cosine alpha pi equals to minus 1, and consequently the separation distance increases compared to classical particles, implying the existence of quantum repulsion force between them. And for anyons where alpha situated between 0 and 1, we have two situations with respect to alpha. Anyons with alpha between 0 and 1/2, the cosine of alpha pi is a positive, which means that the separation distance reduced, indicating a quantum attraction force between anyons, and we have a bosonization phenomena. And for anyons with alpha between 1/2 and 1, the cosine of alpha pi is a negative, which means that the separation distance increased, indicating a quantum repulsion between anyons, and we have a fermionization phenomenon. And for anyons with alpha equal to 1/2, the cosine alpha pi is cancelled, which means that the separation distance matches that of classical particles, indicating that there is no quantum force is present. As a consequence, it is worth mentioning that these effective forces observed in quantum mechanics, which lack a classical counterpart, are not forces in the real sense, but rather a consequence of the geometrical requirements of wave functions. As a conclusion, in this work, we developed a comprehensive theoretical framework to describe the quasi-particles that exist between bosons and fermions, particularly in two-dimensional quantum systems. Our investigation revealed that the unique quantum properties of these quasi-particles influence the mean separation distance between particles pair, leading to the emergence of novel quantum effective forces. Specifically, we found that anyons behave as bosons for the interchange phase parameter alpha between 0 and 1/2, and as fermions for alpha between 1/2 and 1, and as classical particles for alpha equals to 1/2. As a perspective, we suggest that future research could use the generalization of the concept of anyons from two-dimensional system to fractional particles in any dimensional space through the dynamical and statistical mechanics approach. This approach will deepen our understanding of how these particles affect the stability to diverse physical systems through the mechanism of gravitational instability. And thank you very much for your attention.